Now that we know how to draw basic Lewis structures, in this lesson we're going to look at Lewis structures that have atoms that are exceptions to the octet rule. That's right, they don't have 8 electrons. And for most of them we're going to try to explain why they can get away with not having 8 electrons. So let's look at it. Now the rules for drawing Lewis structures aren't going to change at all. Matter of fact, that's a bad place. I guess we're going to go down here. So let's start with water. Water is an example of an atom that has an exception to the octet rule. But nothing's going to change about the beginning part of it. I need you to add up the total number of valence electrons that we're going to use in this molecule and type it in now. Okay, so hopefully you got each H, and there were 2 of them, right? Is contributing 1 electron, right? Because it's in the first row. Remember, 1, 2, 3, 4, 5, 6, 7, 8. And the most valence electrons you can ever have is 8. There's only 1 oxygen, and let's see, 1, 2, 3, 4, 5, 6. And so 6, 7, 8 comes out to 8, and it's a nice even number, so I'm feeling confident in that. Which element do you want me to put in the middle? Oxygen. There's only 1 oxygen. That's absolutely right. So that's what goes in the middle. Now I will tell you that we are eventually going to lead up to another way to tell which element goes in the middle, a better way which has to do with electronegativity. But we'll see that coming up a little bit later. Okay, so that's what it looks like. Now you guys know I start on the inside or outside? Definitely the outside. So I'm going to go to the outside. Now as soon as I start putting electrons on this, I'm doing something wrong. And the reason is because hydrogen is an exception to the octet rule. Hydrogen is only allowed to have the 2 electrons in the bond. Why? Well, let's get to why that is, but let me erase my my extra electrons here because it's making me feel bad about stuff because I know that's not right. Let's see. So yeah, if you ever see hydrogen, hydrogen can never have electrons on it. It will never look like that. It will just look like this. It only gets the 2 electrons in the bond. Well, the reason is because it is satisfying the octet rule. Remember that the octet rule, it was not really saying that all atoms need to have 8 electrons. It says all atoms will gain or lose electrons to become isoelectronic with a noble gas. Well, obviously, if you're talking about oxygen, oxygen does need 8 electrons. It has 6 valence electrons, and it would need to gain 2 to become isoelectronic with neon, just like chlorine would need to gain 1 to become isoelectronic with argon. But think about hydrogen, right? Hydrogen has 1 electron, 1 valence electron, and it only needs to gain 1 more to become isoelectronic with helium. Helium is the only noble gas that has 2 electrons. So that's why hydrogen is an exception. It's not really an exception to the octet rule, but it does have less than 8 electrons. So this is what I would call an electron deficient atom. And deficient, I mean does not have enough. You know, if somebody said, you know, Mr. Jones, his charisma is a bit deficient, what they'd say is, I'm not very charming, right? Hey, you want to help pay for dinner? I'm deficient in funds right now. In other words, I don't have any money. I don't have enough money. So electron deficient atoms don't need a full octet. And it turns out there's 2 of them. It's not just hydrogen. There's also boron, which we're going to get to in just a second. So we've established that this is not what we do with hydrogen. It's the only element that can only have 2 electrons. By the way, something else you'll see, because it only can have 2 electrons, you'll never see hydrogen in the middle of a molecule because you could see it would have to have 2, 4, 6. You would have to have more than 2 electrons to be in the middle. So you'll never see it anywhere but on the outside, and it doesn't get dots. It doesn't get electrons. All right, so that's good. So that means we've done the outside. Hydrogen is done. Now, we've used 2 4 electrons. So we've used 4. I'm going to subtract 4 from this. That tells me I've got 4 electrons left. We've done the outside now. We go to the inside. And the good news is oxygen needs 2 up there and 2 down there. And that uses up our last 4. Check to make sure oxygen has an octet. It has 2, 4, 6, 8. It does. Check to make sure hydrogen has an octet, and in its case, that means just the 2 electrons in the bond. It does, so we are done. If I was going to ask you how many lone pairs are on the central atom in this molecule, what would you say? 2. That's absolutely right. And don't forget, on the central atom and central atom only, I typically put an orbital loop. And you'll see when we get to shapes later why that's particularly important. Okay, hydrogen is the first exception to the octet rule that we're going to have. It never gets electrons on it, and it's always an outside atom. Now let's go look at boron. So boron is the other electron deficient atom. Now boron's a little bit different though, and it's a little bit harder to explain, but not adding up the valence electrons. Quickly, add up the valence electrons I'm going to need in BF3. All right, I have fluorine. Fluorine gets 7 valence electrons, right? 1, 2, 3, 4, 5, 6, 7. There are 3 of them. 7 times 3 is 21. So you see I didn't write it out that time. I don't most of the time because you understand the concept now. Boron, 1, 2, 3. Boron only gets 3 electrons, so that's a total of 24. Hey, that's a good number because it's even. Now maybe I added it up wrong and it was accidentally even, but it makes me feel good about it. Which element goes in the middle? Boron. I'm going to spread out my fluorines. Hey, by the way, before I've done anything else, how many electrons are already in the molecule just by connecting it? 6 electrons. That's absolutely right. 2 in each bond. There's 2 electrons in each covalent bond. All right, I'm going to start on the outside. I won't ask you that because you guys know that. And I need some on the top, left, and bottom. Left, bottom, right. And that gets to 8 electrons around each one, right? Always start on the outside. Fluorine has to obey the octet rule, so it needs 8 electrons. Now we've used 2, 4, 6, 8, 10, 12, 14, 16, 18, 20, 22, 24. We've used them all. But does boron have a satisfied octet? No, it only has 2, 4, 6 electrons. It has an empty orbital up here on the top, right? You imagine your electron dot model. Remember, there's an empty orbital up there on the top. So boron is the second exception. And those are the only 2 elements that can get away with less than 8 electrons. Hydrogen, you remember, never has any lone pairs on it. It only gets the 2 in the bond. And boron, now here's the emphasis I'm putting, can have 6 electrons if required. Is the only element on the periodic table that can have less than 8 electrons and doesn't have a satisfied octet. But you should know that there will be many cases where boron actually does have an octet, and don't let that throw you off. But if you get to the end here and boron does not have a satisfied octet, you can let it go. It's no big deal. We are done. And so how many lone pairs are on the central atom? None. There's absolutely none on there, right? There's 3 bonds and no lone pairs, and we're absolutely done. So it's pretty unusual. Now, I will tell you, if this wasn't boron, if this was some element, other element, like let's say we had gotten to this point and it was a sulfur or something like that, you cannot leave sulfur with an empty orbital. It's only boron. If this had been oxygen in the middle or nitrogen, you cannot leave it. But if it's boron, you can leave it. Now, that, of course, will probably leave you with the question, well, what do I do if it's not boron? And that's coming up in the next lesson. That's not in this lesson, and that will happen, by the way. But if it's boron, just let it go. But it does have to have 6. It can't have 4. Okay, so those were the 2 electron deficient atoms. Now we're going to show you a different kind of violation of the octet rule here. And I will tell you, if I never taught you about this exception, most people don't even notice it. It's not a big deal. There's not really anything you have to do that's special, but we want to explain what's going on and why. So this compound is going to exemplify it. And you don't have to do anything different. What I want you to do is count the valence electrons, draw on your paper the entire Lewis structure, and I want you to tell me how many lone pairs are on the central atom. The central atom's argon, by the way. How many lone pairs are on that argon? Yeah, it's weird, right? It's really weird. So if we were to add them up, argon, by the way, if you're thinking that's a noble gas, it contributes 8 valence electrons. What the heck is a noble gas doing in a compound? It's true, noble gases generally don't react, don't end up in compounds, but with enough pressure and heat and all that, you can get them to react. Each fluorine is going to contribute 7 valence electrons, right? Remember, we count over 1, 2, 3, 4, 5, 6, 7. And that's going to give us, let's see, 7 plus 7 is 14. 14 plus 8 is 22. It's an even number, seems reasonable. I just want to make sure I'm adding correctly. Argon goes in the middle. And we start around the outside. Fluorine does need an octet. It's not hydrogen. It does need an octet. Goes like that. We've used 2, 4, 6, 8, 10, 12, 14, 16. We've used 16. So if I subtract my 16 electrons, how much do I have left? I have 8. Is that right? 4. Nope, 6. Not 8. 6. Okay. Now we've got to go to the inside. Now you might be sitting here thinking, hold on, argon has electrons filled there with the bond and there with the bond. It only has 2 more empty orbitals. And you would be not correct on that. And I'm going to show you why. So watch what happens here. I have 6 electrons. I come to the middle. I'm going to put 2 here, but I still have 4 more. I'm going to put 2 there, and I'm going to put 2 there. Notice how I'm putting them in pairs. And it might be bugging you because it feels like I just created an extra orbital down here on my electron dot diagram. And I did. So let's explain why. Well, argon is an example of a compound that I would call has an expanded octet. It has more than 8 electrons. 2, 4, 6, 8, 10. We've used all the electrons, and that's okay. Any atom that's in period 3, 4, 5, 6, and 7, in other words, isn't in these two. You can't do it here. You will never see carbon with more than 8 electrons or nitrogen with more than 8 electrons. But if it's below this line, it definitely can have more than 8 electrons. But only if it's a central atom. It's got to be a central atom. Okay? This is what we refer to as an expanded octet compound or element. Expanded octet just means more than, right? If we expand your living room, you've made it bigger, right? That kind of thing. That's all that means. And it has more than 8 electrons. So we call it an expanded octet atom. So let's get to why. The reason why, let me see if I can get a different color. The reason why is because what's happening is, you remember that these are the 3p orbitals. These are the 2p orbitals. Well, if you're looking at argon here, right, argon will fill its 3p orbitals, and that gets it to 8 electrons. And you might wonder, how the heck is it going to add more than that? And the answer is, right here, you'll remember, are the d orbitals. And they're not just the d orbitals. Remember, we've got 4s and we've got 3d. They're the 3d orbitals. And it turns out the 3d orbitals are not much higher in energy than the 3p orbitals. So argon, confronted with all these extra electrons, can pile them into the 3d orbitals. But if you think about this, if we were to go look at the 2p orbitals, why can't nitrogen have more than 8 electrons if it's in the middle? Because when it fills up to 8 right here, if it has more electrons coming in, does it have the opportunity to fill the 2p orbitals? Or I'm sorry, the 2d orbitals. And the answer is no, there are no 2d orbitals for it to pile in extra electrons. Unlike the ones that are in row 3, they have 3d orbitals to pile extra electrons in. If you're in row 4, the 4p's can pile electrons into the 4ds, and you get the point. So that's why any atom that's in period 3 through 7, in other words, it's not in period 1 or 2, can have an expanded octet. But you're never going to see carbon do it, or nitrogen do it, or any of those. Okay, so let's try another one. We're going to do SEH2. So I want you to add up the valence electrons and type them in here. Let's make sure that we agree. Se should have, let's see, 1, 2, skip the middle, 3, 4, 5, 6, should have 6 valence electrons. Each H should contribute 1 valence electron. Okay, now that we know what our total is, I want you to draw the Lewis structure and answer this question. Did you notice that this one was not an expanded octet, but it had hydrogen that had a deficient octet, right? So we go like this, we go around the outside, but remember, no electrons on that hydrogen. I can't do that because it already has the 2 electrons in the bond. That makes it isoelectronic with helium. We're done with hydrogen. Did you remember that? All right, let me get my, not highlighter, pen. And so then we go to the inside. Right now, how many electrons are on this selenium? 4, that's right. It has an empty orbital on top and bottom. We've used 4, so that means we have 4 electrons left. I'm going to put 2 on the top and 2 on the bottom. Selenium is not an expanded octet atom. It has 2, 4, 6, 8. It's just a normal octet atom. But what we're getting out of this one is that hydrogen, no electrons on the hydrogen. Super important. Okay? Let's do one more. Let's do PCl5. Add up the valence electrons and type them in. Did you get phosphorus had 5 valence electrons? 1, 2, Oop, 1, 2, 3, 4, 5. And each chlorine, forgive me for not writing out all the chlorines, contributed 7. But there were 5 chlorines, so 7 times 5 is 35. If I add up 35 plus 5, I get 40 valence electrons. Wow, that's a lot. All right, draw the Lewis structure, and when you draw the Lewis structure, remember, follow all the rules on the screen, and then I want you to answer these questions. Let's see, I'm going to spread out my chlorines. Really not super important how I do this, as long as I make sure I get 5. Sometimes people only put 4. Make sure you count carefully. And then we start on the outside. So I'm going to do my electrons on the outside. I'm going to pause the video so you don't have to watch this. Okay, so that means that I've got 8 on each one. 2, 4, 6, 8. 2, 4, 6, 8. 8 times 5 is 40, and we are done. We've consumed all of our electrons. We go to the inside and check and see how many electrons are on that phosphorus right now. Okay, is it a deficient octet or an expanded octet? It's definitely an expanded octet. It has 2, 4, 6, 8, 10 electrons on that phosphorus. But that's okay because phosphorus is right here. It's filling up its 3p orbitals, and it can put them where? The 3d orbitals. That's absolutely right. It can do it because it's in row 3, 4, 5, 6, or 7. The only ones that can't are in row 1 or 2. All right, let's try this one. Add up the valence electrons, type it in here. Boron contributes 3. Each hydrogen contributes 1, but there are 3 hydrogens, so that's 3. 3 plus 3 is 6 electrons. That is not a lot of electrons. All right, draw the Lewis structure and describe to me what it looks like. Boron goes in the middle. We're going to put our hydrogens around it. All right, we start on the outside. We've already used 6 electrons. Oof, we've already used them all. Is that okay? Yes, because hydrogen doesn't get any electrons on the outside. It only gets the 2 in the bond because it's an electron deficient atom. And boron doesn't have 8 electrons. Right now it has 2, 4, 6. And boron is the other electron deficient atom. It can get away with just those. All right, in our very last one here, I want you to add up the valence electrons we're going to use in this one. I will tell you that sometimes people worry about which atom, hydrogen or chlorine, because it's not HCl. It's H and Cl. There's only 2 atoms. People worry about, well, what's the inside? Trust me, don't worry about it. Just work on it. Add up the valence electrons. H contributes 1. Chlorine contributes 7. 1, 2, 3, 4, 5, 6, 7. That's a total of 8 electrons. We go HCl, and we decide which one's in the middle. It doesn't really matter because hydrogen is not going to get any extra electrons. So then we just have to satisfy the octet of chlorine. We've used 2, 4, 6, 8. We've used them all. Chlorine has an octet. Hydrogen has an octet too. It just only has 2 because it's trying to be like helium, and we're done.